natural number n which is not equal to 1. Okay, and because f is analytic and also g is analytic, the function f minus g is analytic, and the functions f and g, they are equal on which set? They are equal on the set 1 by n, where n is greater than or equal to 2. So the set of all points z in D such that f of z equals g of z contains the set 1 upon n, where n is greater than or equal to 2. And we know that the set 1 upon n greater than or equal to 2 has a limit point, namely 0. So because 0 is a limit point of the set, 0 is a limit point of the set z in D such that f of z equals g of z, and 0 is an element of the domain. And therefore, by a corollary of identity theorem, what do we get? We get that f and g are equal, means f of z equals g of z for every z in D. But what is g of z? G of z is z upon z plus 1, and thus we have shown that f of z equals z upon 1 plus z for every z in D. So we get the only function f which is of the form z upon 1 plus z, which is analytic and satisfies the given condition. Okay, so now I'm giving you exercise. By the same way, we need to find out all analytic functions f from D to C which satisfy f of 1 by n equals n upon 1 plus n. See, one can again guess the formula for f. F of 1 by n can be written as 1 upon n plus 1. So the function f of z should be 1 upon z plus 1, and by the same way you can complete or you can write the solution of this exercise. Okay, so next example, does there exist an analytic function f on the open unit disk which is 0 only on the set 1 upon n belongs to n minus 1? In fact, we show that there is no such function. So the answer is no. Now let us see a solution. Suppose that f is such a function. Means what? The function f is analytic on D. F vanishes only on the set 1 upon n belongs to n minus 1. It means what? See, because the function vanishes only on this set, means the set of zeros of f is the set 1 upon n belongs to n minus 1, and the set zf means 1 upon n belongs to n minus 1 has a limit point, namely 0, and which is in the domain, and therefore by identity theorem the function f is a 0 function. So because it is a 0 function, it is going to vanish at every point, and we are interested in finding out which function. We are interested in finding out a function f which is 0 only on this set. But we have shown that if a function f is 0 on the given set, analytic function is 0 on the given set, then that function will become identically 0, and thus no such function exists, right? Okay, so now let us go for the next example. So let D be a domain and let f and g be holomorphic on a domain D. Holomorphic means analytic functions, and also we are given that f power n equals g power n for some n belongs to n. It means what? Fz into fz into fz n times equals gz into gz into gz n times for every z in a domain D. Then we want to show that f equals alpha times g for some alpha in C which satisfies the condition mod of alpha equal to 1. Okay, so let us see how we do this. So we are given that f power n equals g power n. But if we simplify, I mean, if you know how to factorize x power n minus y power n, then we are going to get f power n minus g power n equals f minus g, f minus omega g, f minus omega squared g, up to f minus omega power n minus 1 into g, where what is omega? Omega is the nth root of unity. यहाँ पे जो n है यहाँ ऊपर आना चाहिए, नहीं, it should be in the division. Omega equals e power 2 pi I by n. It is the nth root of unity. फिर से बता रहा हूँ, omega is what? E power 2 pi I by n. Okay. Now because f is analytic, g is analytic, so all these functions f minus g, f minus omega g up to f minus omega power n minus g, they are all analytic functions and their product is 0. So by using the first example, what is the first example? We have seen the first example that if f into g is 0, then either f is 0 or g is 0. So by using induction, one can prove that if we are given n analytic functions, say f1, f2 up to fn, which are analytic on a region G, and if the product of those n functions f1, f2 up to fn is 0, then at least one of them is a 0 function. So if we use that fact, what we get? So now we are having this 0 means the product of all these n analytic functions is 0, and so one of these n functions must be 0, and therefore there exists some k between or in the set k in 0, 1 up to n minus 1, such that f minus omega power k g equals 0. And because omega has modulus 1, omega power k has modulus 1, and thus we have shown that f equal to omega power k into g, and omega power k has modulus 1. So the alpha which we are requiring is omega power k. Let us see next example. Let f from d to c be analytic, and we are given that f of z equals f of z squared for every z in close 0 open 1, and then we want to show that f is a constant map. Okay, so again, to prove f a constant map, if we can show that f is a constant map on some set which has limit point in D, then we are done. Just we need to use identity theorem. So we start with any x which is between 0 and 1. Then one can see that f of x is same as f of x squared, but f of x squared is same as f of x squared squared, that is same as f of x squared square squared. So for each n we are going to get f of x equals f of x power 2 power n, and because x is in the open interval 0 1, x power 2 power n tends to 0 as n tends to infinity, and because f is continuous, what we are going to get? We are going to get f of x power 2n tends to f of 0, but f of x is same as f of x power 2 power n for all n, and therefore what do we get? F of x equals f0. And what we have shown, I mean, this is what we have shown for every x in open 0 1. And so now we define a function g from d to c by g of z equals fz minus f0, right? Then one can see that actually I should write here g, then g is analytic on d, and 0 1 is subset of zg, means the set of zeros of g. Why? Because if we take any x from open 0 1, then g of x equals fx minus f0, and already we have shown that for any x in open 0 1, fx is same as f0. So open 0 1 is contained in the set of zeros of g. The function g is analytic and d is domain. Now the set open 0 1 has a limit point 0, or you can also say 1 by 2. In fact, any close 0 open 1, every point of close 0 open 1 is a limit point. See, we are talking of limit point which is inside D. In fact, 1 is also limit point of D, but we are not interested in that one, because we want a limit point which should be in the domain. So the set open 0 1 has a limit point in D. That means the set of zeros of G has a limit point in D. So by identity theorem, G is a zero function, right? As 0 is a limit point of open 0 1, and hence it is a limit point of Zg. So by identity theorem, G is zero map, and that means what we have shown? We have shown that f of z is same as f of 0 for every z in D. So f is a constant map. Let us see the next example. Let f from D to C be analytic, and let Zn be a sequence of distinct points in D converging to 0. That is given. We are given a function f which is analytic. We are given a sequence of distinct points in D which is converging to 0, and also we are given that for each of these points f of Zn is same as f of minus Zn, and then we have to show that f is an even function. Means we need to show that f of z equals f of minus z for every z in D. Let us see how we do this. So we define a function g from D to C by g of z equals f of z minus f of minus z. So our interest is to show that the function g is a zero function. Obviously f is analytic, minus z is analytic, so composition is analytic, and therefore the function g is analytic. And one can also see that the set Zn is contained in the set of zeros of G. Why? That is the hypothesis, na? F of Zn is same as f of minus Zn. So G of Zn is f of Zn minus f of minus Zn. That will become 0. So this set is contained in set of zeros of G. Now because Zn's are all distinct, that is given, and the sequence Zn is converging to 0, what we get? 0 is a limit point of the set Zn, and 0 is an element of the domain, and therefore by identity theorem G is 0, and thus we have shown that f of z is same as f of minus z, and that proves f is an